We're back. Part 2, planes in space. Today in part 2, we'll be doing distance between a point and a plane. So let us say that we have a plane thusly. Let's call that plane Q. And there's a point P, X, Y, Z, not on it. And there's some point here, P naught, X naught, Y naught, and a Z naught. And there's a perpendicular vector here that's ABC, right? Then if you're looking for this distance right here, let's call that D. And that D will basically be P naught P vector, the magnitude, times the cosine theta. Now, if you remember earlier, when we had two vectors, let's say this vector right here, guys, right? If this has angle theta, and that will be angle theta, because they have, normal right here as well. Cosine theta was defined by dot product of n, p naught, divided by the magnitude of both. Well, you know that this cancels right here. Oh, by the way, before I go any further, you should note that cosine of theta can be negative, which means that distance in this equation is negative. So whatever result we get, we need to put an absolute value around it. I'm not going to do it right now because the round's getting a little messy, but you understand I'll be doing that at the end. So the A is defined to be ABC, dot product. Normally I'll be very careful to which one I subtract first, but because I'm going to be taking absolute value, I don't really care at this point. So that'll be, I just like to have the x in the first, x minus x naught, y minus y naught, z minus z naught, divided by the magnitude of the n vector, which is a squared plus b squared plus c squared. Okay, so I just applied the dot product, and it yields that. So what I'll do is I will expand that out even further. Having expanded out this term right here, guys, I end up with this, but in the past we understood that this expression would replace that as a d. Once I replace the value of the d here, guys, that's what I get. And as I mentioned earlier, the cosine could be negative, but distance cannot. So I actually need the absolute value around the whole thing. So that's why you see this right there. So that is indeed the equation, or I should say formula. This is a distance formula, guys, between point and plane. Let's do an example, shall we? Example, find the distance from point 201 and the plane x minus 2y plus 3z plus 5 is equal to 0. Well, looking back, guys, we need to look at the formula right here. Now that we developed it, I don't have to develop it all over again. So essentially, we have equation for this right here, plane, and we got a point right here, 201, that's not on it. And I'm looking for that distance right here, guys, okay? So we went through some fancy derivation to find that formula. Now that we have it, we should use it. So the d is equal to, oh, by the way, this x, y, z stands for this one, x, y, z. And this right here, this 1, -2, 3, is the component for the vectors. 1, the normal vector, which is also the coefficient of x, y, z. The way you apply this is essentially copy this over. So essentially I copy this formula over here, and then I copy the coefficients of the x, y, z down here to find the distance. And the x, y, z you replace with the point x, y, z, which is 2, 0, and 1. When you go through the math, it comes out to 10 over square root of 14. And it is that straightforward, guys. Good luck.